So I would like to take this moment to welcome you to the video series that I am calling Not the Ideal Medium for Teaching Physics 2020. So we're going to start just as kind of a practice video going over chapter 17. We've already gone over most of it, but I want to get a video up there before I want to do a test video. So we will do the notes for chapter 17 like this. Okay, so let's start with, right on with chapter 17. What is light? So we've already seen that light behaves like an electromagnetic wave. We saw that in the last section. So light is oscillating electric and magnetic fields that are perpendicular to each other. So before Maxwell, there was a great debate over whether light was a particle or a wave, because there seemed to be evidence for both. They came up with two models, and then Maxwell was able to combine them. So the first one that we have is called the wave model. So the wave model explained diffraction. So treating light as a wave made it make sense that light could bend around corners, it could interfere with itself, things like that. So a lot of people saw light as a wave. This treated light as an EM wave. The next model that people used was called the Ray model. This explained how light would reflect and refract. That's when you see it doing weird things in mediums. This saw light as a particle. Both of these models made sense to fit certain criteria for light, but both of them broke down at a certain point, which is when we came up with the photon model. The photon model explained the wave and particle attributes of light. So this treated light as discrete units of energy called quanta. So light came in individual units. It wasn't just infinitely indivisible. You had units of energy called quanta. This saw light as quantum mechanical, which essentially meant that it got weird really fast. One of the first things that we're going to talk about is refraction. So refraction can be seen, so light seems to slow down in materials due to interacting with the other atoms. The effect of this slowing down is called refraction. The effect of this appearance of slowing down is called refraction. It's quantified by something called the index of refraction. So the index of refraction. This is symbolized by the letter n, a lowercase n. This is exactly what you dealt with if you took Regents physics. So this is the same idea. The way that we come up with this n value is we say that n is equal to c over v, where c is equal to 3 times 10 to the 8 meters per second, the speed of light in a vacuum, and v is the speed of light in the material. These are some standard indices of refraction. So the index of refraction of a material does not change. It is the essence of that material itself. A vacuum is defined as 1 exactly. There's no slowing down of light. So C over V would just be 310 to the 8 over 310 to the 8, index of 1. Air is pretty close, so it's 0.0003. So we say we treat air as a vacuum. So we say that the index of refraction of air is 1. Then we get to water, which is 1.33, glass, which is 1.5, diamond 2.42. The only ones that I would expect you to know are air, which is you use just air as 1, treat air as having an index of refraction of 1, 1.0, and glass, 1.5. Anything else would either be given to you or you would be able to directly solve for it. So when light encounters a boundary, so we have a vacuum, and then we have a medium, and then we have another vacuum. So the light goes through the medium, and at the boundary, velocity and wavelength both change. But frequency does not. This allows the wave to be continuous. So if you see here, we've got the same light wave. In the vacuum, we've got a certain wavelength. So this is going from crest to crest. In the medium, we have a different wavelength, a different lambda value. Again, measured from crest to crest. When it re-emerges, it has the same wavelength as before. Here it's trough to trough, but same idea. So the wavelength only changes when it's going through the medium. It doesn't change the wave itself. So if we want to find this new wavelength, we start with N equals C over V. From there, from previous wave equations, we're able to say that the speed of light, so a velocity is equal to, so the speed of light in a vacuum is equal to its wavelength in the vacuum times its frequency. This is from, I guess that would be, so that would be like frequency equals velocity over wavelength. So something like that. We're just able to get that from there. Erasable pens are the best. And then in the medium we have lambda in the medium times the frequency of the medium. Now, as we said from before, frequency does not change. Frequency stays the same. So we say that the frequency in the vacuum is equal to the frequency in the medium. This leads the frequencies to cancel out, giving us that N equals lambda vacuum over, that's not how you make that letter, lambda vacuum over lambda medium. Rearrange it for funsies, and we get that lambda medium, so the wavelength inside the medium is equal to the wavelength in the vacuum divided by the index of refraction. Orange light with a wavelength of 600 nanometers is incident on a 1 millimeter thick sheet of glass. What is the light speed in the glass? So, as I said before, index of refraction of glass is one that I want you to know. So that is 1.5. We want to find the velocity of light in the glass. We want to find the speed of the light in the glass. So to do that, we're going to do V sub g, velocity of light in the glass, is equal to C over N sub g. This is from that first equation on the first page, or the last bold equation on the first page. C is 3 times 10 to the 8 meters per second, and G is 1.5. So instead, I will not leave you in suspense. So the velocity in the glass comes to 2 times 10 to the 8 meters per second. So the velocity of the light in the glass is 2 10 to the 8 meters per second. So now we want to know how many wavelengths are in this sheet. You know, because that's a thing that people wonder about. So we can say that lambda in a vacuum is equal to lambda in air. We treat a vacuum and air in the same way. So that is equal to 600 nanometers. From just above, we have lambda glass. In this case, using this equation, the medium is glass and the vacuum is the vacuum. So lambda G equals lambda vacuum or air divided by index of refraction in glass equals 600 nanometers over 1.5. That gives us a wavelength of 400 nanometers in the glass. The question was asking for how many wavelengths of light are in the glass. So we were able to say that the number of so n wavelengths span a distance of d. So we can say d equals n times lambda. D is equal to 1 millimeter. Gave that an extra sig fig for funsies. Using that, we can say n is equal to 1 millimeter over 400 nanometers, giving us 2,500 wavelengths. So there are 2,500 wavelengths of light in this slab of glass. That is going to conclude part 1. Tune in for part 2, the sequel.